Welcome to another explainer where we dive into the papers that really shaped the field. Today, we're breaking down one that solved a huge headache in computer vision: how to get a computer to see both the big picture and the tiny details all at the same time. So think about it. How does a self-driving car spot this massive truck right in front of it, but also see a tiny pedestrian way down the road? This is what's called the multi-scale problem, and for a long time, it forced developers into a completely impossible choice. So here's how we're going to unpack all this. First, we'll really dig into why this multi-scale thing is so tough. Then, we'll look at some of the clever but kind of flawed early attempts to solve it. And that's going to lead us right to the main event, the feature pyramid network. We'll see how it works, how it completely blew away the competition, and of course, the legacy it left behind. Right, so here's the core issue. To recognize a whole building, you need to see its overall shape, the windows, the roof line. But to recognize a single brick in that building, you need to see its texture up close. Well, a deep neural network really struggled to do both at once. The big picture features were just too blurry for the details, and the detailed features, well, they completely missed the wider context.
And this created this classic trade-off. You could have a model that was incredibly accurate, but oh my gosh, it was painfully slow, kind of like the tortoise. Or you could have one that was super fast, ready for the real world, like the hare, but it would just constantly miss all the small but important stuff. It really felt like you just couldn't have both.
So how did researchers even try to solve this? Well, the main idea for years and years revolved around this concept called a pyramid.
The classic approach was what's known as the featurized image pyramid. You take your original image and you just resize it into a bunch of smaller versions, and then you'd run your analysis on every single one. Now, this worked great for accuracy. You got these rich, detailed features at every single scale. The problem? It was computationally brutal, just absolutely brutal. Processing the same image that many times made it way too slow for any real-world use.
Okay, so to get that speed boost, popular object detectors like FastRCNN, they went in the complete opposite direction. They decided to use features from just one layer deep inside the network. And yeah, it was way faster, for sure, but it came with this huge downside. Small objects basically just became invisible in that low-resolution data. Accuracy, especially for the small stuff, just went right out the window.
Then someone had a really clever thought. A network already creates features at different scales as it processes an image, right? So why not just use all of them? It sounds like you're getting them for free. Models like the single-shot detector, or SSD, they tried this. But there was a catch. The early layers, the ones with all the high-resolution detail, they had a pretty weak semantic understanding. They could see edges and colors, sure, but they didn't really know what they were looking at, like whether it was a person or a car.
And this is where this paper just changes everything. It proposed this beautifully elegant solution called the Feature Pyramid Network, or FPN for short. The goal was simple, but it was also super ambitious. Create a feature pyramid that was as fast as those single map methods, but as powerful as that super slow image pyramid. They really wanted the best of both worlds.
So how does the FPN actually pull this off? How does it work its magic? How do you create a feature pyramid that has rich, meaningful information at every level without doing all that slow, repetitive processing? It all happens in three key stages. First, you have the bottom-up pass. This is just the normal thing a ConvNet does. It analyzes an image and creates features that go from fine to coarse. But then, the magic happens. A top-down path takes the most abstract, high-level understanding from the very end of the network and starts working backwards, upsampling it. And finally, these lateral connections act like bridges, merging that rich what-is-it information from the top-down path with the precise where-is-it information from the bottom-up path.
I love this. The authors use this fantastic phrase to describe what's going on. They say the top-down path essentially hallucinates what these high-level concepts would look like if they were at a higher resolution. And then that lateral connection comes in and uses the actual high-res features from earlier in the network to ground that hallucination in reality. It's brilliant. It's how you combine the what with the where.
And the core building block that makes all this possible, it's surprisingly simple. There's no crazy, complex math here. The high-level map gets upsampled, the detailed map gets a little tweak from a simple convolution, and then they're just added together. That's it. That simple act of addition is what merges these high-level concepts with precise location, creating a brand new, powerful feature map at every single level.
Okay, so a clever idea is one thing, but did it actually work?
Well, to prove it, the authors plugged FPN into two of the leading frameworks at the time, faster RCNN, which was a really powerful object detector, and its sidekick, the region proposal network, which is the part that finds potential objects in the first place. This study right here is so telling. Just look at the full FPN model in that first row. It gets an average recall of 56.3. Now look what happens when you take away the top-down pathway, or you take away those lateral connections. The performance just tanks, it completely plummets. This is the proof. It shows that both of those components are absolutely critical to making this whole pyramid idea work. You need both. You need the semantic info from above and the localization info from below.
The final numbers were just staggering. Just for generating proposals for where objects might be, FPN boosted the average recall by a massive 8.0 points over a really strong baseline. I mean, that's a huge leap forward, especially for finding all those tiny objects that other models would miss.
And when they plugged it into the full detector, FPN improved the overall accuracy on the industry-standard COCO benchmark by 2.3 points. Now, 2.3 might not sound like a lot, but believe me, in this field, against those kinds of benchmarks, that is a gigantic leap forward.
But honestly, here's the most impressive part. With this one architectural change, and without any other fancy bells and whistles, a standard, faster RCNN with FPN beat every single other single-model submission on the COCO leaderboard. We're talking about the heavily engineered models from the 2015 and 2016 competition winners. It just completely reset the state of the art.
But the impact of this paper went way beyond just those initial leaderboard results. It really fundamentally changed how the entire field thought about the problem of scale.
You see, FPN's elegant and efficient design meant it was quickly adopted not just as some clever trick, but as a standard fundamental building block in pretty much all modern object detection architectures. And its usefulness quickly spread to related tasks like instant segmentation and keypoint estimation. It finally delivered on the promise of multi-scale detection that was both super accurate and fast enough to actually use in the real world.
So a paper this foundational, it naturally makes you ask, okay, what's next? Where can we take this core idea of an in-network pyramid? Here's a final thought to leave you with. FPN uses a fixed, rigid structure for its top-down path and its lateral connections. But what if a network could learn to build that pyramid dynamically for each individual image? You know, if it saw a big landscape with tons of tiny objects, maybe it could decide to strengthen that hallucination pathway. Or, for a detailed close-up, maybe it could widen those lateral bridges to pull in more texture. An adaptive, content-aware pyramid. That's an idea that flows directly from the legacy of this amazing paper.
And that's just one idea this paper sparks. We really encourage you to read the full paper yourself to appreciate all the elegant details and the rigorous experiments they ran. We've dropped a link for you down in the description.
This is for entertainment purposes only.